Hello everyone, I'm honored to be online for this conference. Please let me do a brief introduction of myself. My name is Yuanzhi. I'm from China and I'm currently a master student at Nanjing University of Aeronautics and Astronautics, and I'm currently doing some research on computer vision. By the way, I highly recommend everyone to visit China. And if you want to learn about some acts in the Chinese traditional country, Nanjing is a very worthwhile place to visit. Back to the main story. Today, I would like to share with you some of my research progress on traffic sign detection. The article title is named A Single Level Detection Model for Traffic Sign Detection using Channel Shaft Residual Structure. If you have any question to share after I finished my report, you can contact me through the email below. Here. My presentation is structured in the following ways. First, I will give an introduction to the paper, including the background, problems, and our goals. Then, I will move on to our solution and strategy for this. After that, I will present the result of some experience. And finally, I will have a conclusion to the essay. First, I would like to give you a bit of background. So, why did we conduct this research? This is a good question. Our paper is finished in the context of autonomous driving. It mainly concerns the traffic sign recognition system. We refer to it as TSR. The study of TSR is important because TSR is a critical component of unmanned driving system, and high-defined maps which can provide TSR aims to help make drivers more aware and able to make better safe driving decisions. So it needs to satisfy the two special features: high precision and real time. Then we can organize what features the traffic sign have. We can see the figure 1. Figure 1 shows some very common traffic sign contains 3 common types: danger, prohibitory, mandatory. You can take a look at the picture and we can easily find two features. One, the same kind of traffic signs are very similar. And two, their internal structure is very complicable. Here the third and fourth point are the problem we will face with the traffic sign we see on the article road. There will be a lot of similar background interference in the image, where the effect of natural environment, such as rain, haze. Of course, another big feature is that the traffic sign show very small areas in the image. Table 1 gives the introduction of Tsinghua 100 dataset, which contains 6,105 images for training and 3,071 images for test. And Figure 2 shows the visualized images of the train seat under the size of 800 times 800, in which we can see that the traffic signs are mainly small and medium targets. Please look here. The definition of small, medium, and large targets will follow the COCO standard. So we summarized some of the difficulties faced in traffic sign detection, including 1. Some traffic signs are similar to each other, and 2. High background interference in the image, 3. Impact of natural environment, and 4. traffic signs are small in the image. After understanding the features of traffic sign and the difficulty of the detection, we investigated some method of implementation, which basically fall into three ways: corner-based, shape-based, and learning-based. We found that the best results were achieved with the deep learning-based approach, so we conducted our research on this basis. Our goal was to get a detection method that could satisfy TSR with high actual and real time, and in fact, we did. Okay, now let me move on to the method section. And because we want our approach to be as fast as possible and to achieve good results, we conduct a pre-experiment that focused on where multi-level features function can improve the detection of small targets. Figure 3 shows our design approach. And we can say C3 to C5 are the input features layers with downsampling multiple 8, 16, 32, and F3 to F7 are the output layers after feature function. And the grid line denotes unusual channels. And we can say in the internal convolutional process, where the 1 times 1 and 3 times 3 are the size of convolutional kernels. There the results of our exploration are shown in table 2. And we found that MIMO, MISO, and sensor achieves comparable performance in TSR. And even sensor structure is the best for small targets. We speculate that the small target information on C3 features layer is detailed enough, and without using the complex information on C4 and C5 layers. We process a real-time yet efficient single-stage detection framework based on sensor structure for TSR. And we can say in figure 4, the backbone is used for features extraction, and the neck further process the features and distribute them to the head. And the head performs the classification and regression task and generate the final prediction result. And then I will then go over their 3 sections in detail. First, in the backbone section, we use convolutional natural networks to build models for extracting features information. And speaking of this, let me introduce the residual structure that it can efficiently solve the problem of granular disappearance and granular explosion caused by too deep network structure. We designed a new residual structure as shown in figure 5. We replace the convolutional residual structure with CS residual structure, and the parameters were reduced by 36.7% with comparable performance. Channel shuffle means that the input channel is broken up, and then we input half of it for convolution, and then concat it to the another half. The detailed description of the backbone network is shown in figure 6 below. The focal model can obtain a two-fold downsampling feature map without information loss, and the CBR models consists of convolutional, batch normal, and reductional functions. Here, We are not going to waste our precious time on the structure section. If you are interested, you can go and read the relevant part of the paper. The input of the neck is the output of backbone. Then in order to make the output features of network neck cover or the target on various scale, we use the dilated convolution to form the residual block, whose root is 2, 3, 5 in order, and we add SE layers to enhance the feature expression after the convolution. If you want to know what is dilation convolution or SE layer, you can find the answer from the reference section. Okay, here's an acknowledgement for our head section on label assignment. And now bring a brief explanation. The definition of positive samples is critical for the optimization of the target detection problem. Based on the pre-generated anchors, we actively use the predicted B-box as supplementary information and propose an adaptive matching strategy. In simple terms, we first fill out some of the positive samples, and then we filter out some of the better ones within that. If you want a more comprehensive introduction, reading the paper or contact me is a good option. We use average precision, we call AP, introduced by the COCO benchmark to evaluate actual and the number of imagined FPS to evaluate the inference speed. We compare our method with other methods, and as you can see in Figure 8, our method has certainly advantages and achieve very good results. And this is a summary conclusion. We can organize this with the help of Figure 9 or Figure 8. In terms of actually our method achieve the highest AP method of 92.9% on dataset, which is 7.4% higher than Euro 14, which indicates that our method has good results for small object detection. And please note, our method is able to research 94.3% if inputting image for inference. In terms of inference speed, input 1800 times 1800 size images under the same conditions. Our method has FPS of 120, which is significantly faster than Euro 14 and further satisfied the real-time requirement. Of course, we also bring some visualization results and show in Figure 9. A left image is the result of our inference, and the right image is the heat map representations of the output features layers. The blue area is the area of interest of the feature map. It is clear to say that our approach has achieved a very good result. Next is the next section where we do a conclusion. In this work, we aim to improve the speed and accuracy of small traffic sign detection, and we find that FBN has limited improvement in detection comparable for small targets. We propose an effective TSR framework detailing various optimization strategies, including for processing CS residue structure, dilated convolutional blocks, and adaptive matching train sample methods. Experiments show that our method outperforms some lightweight detection undergrads on Dataset. Here are some of the limitations we found and plans for future work. Our models have some limitation when facing the detection of very large targets because we focused more on the feature information within a certain range. If you need to, we suggest that you can further increase the range of receptive field or create another bench to detect the large objects. For future work, we will try to optimize the detection on racing using the anchor-free approach, which can eliminate our customization work for anchor and enhance the robustness of the model. Finally, it is important to say that this work is supported in part by the National K-R&D Program of China Undergraduate 2019 YFB 2102000 and impacted by the collaborative innovation centers of novel software technologies and industrialization. In the end, thank you all. On a second note, if you have anything to communicate, you can contact me by email below. Thanks again.